Hi AP Stats, hope you guys are doing all right. We've got one little topic left, and that is comparing two means. The other day we did comparing two proportions, and before that we did comparing, it was matched pairs. It was like comparing two means, but they were matched. So this is our last little bit of info. A few of the things that were cut, because of this whole dilemma, they cut chi-squared distributions from the AP curriculum for the exam coming up, and they cut inference of slopes. So that was the last two little chapters we were going to do, but instead this is the end. Let's do it. This is comparing two means. Means, that would be x bars and mu's. X bar and mu. The difference between comparing two means and matched pairs is when you have two different treatments on the same population. This is two different populations. So you're comparing the means, not comparing the mean difference of the population. My conditions are the same. I've got two random samples. They would have to be independent of each other, and they would need to be normally distributed. Again, the populations would be normally distributed, or I have a large sample size, 30 or greater. If it's less than 30, I would need to look at it to make sure there's no skewness or outliers. Here are the formulas, and they are on the card. Yep, these are x bars and s's. And again, remember that these are t and not z distributions. They're t distributions because I don't know the standard deviation of the population. I only know s, the standard deviation of the sample. Degrees of freedom, we still have that same concept, degrees of freedom. It is still n-1, and it's from the smaller of the two samples. This is a conservative approach. This is the smaller degrees of freedom. Your calculator will actually calculate a different degrees of freedom. You can use either one. Here's a problem. I've already got it worked out, so let's just talk about a few of the key things. This is a problem of two groups, one that received beta blockers and the other received a placebo. And we are measuring pulse rate of patients during surgery. I've got all of these stats here, the mean and standard deviation for one group, the mean and standard deviation for the other group, and I've got 30 patients in each group. Perform a test to see if the beta blockers reduce the pulse rate. I would need to define the variables that I'm dealing with. In this case, I used mu of B for beta blockers and mu of P for, that should say placebo. It says the beta blockers reduce. That's why this hypothesis is less than. The null hypothesis is that they are the same, and the alternative is that it's less than, that it's reduced the pulse rate. My assumptions, I would need to assume that both samples are random and independent of each other. Both samples are 30, so even if the population were not normally distributed, the central limit theorem tells us that the sampling distributions will be normally distributed. Okay, I neglected to, although I should, name this test. This is a two-sample t-test. I can either name it by name like this, or I can name it with the formula. I plugged everything into the formula right here. I got my test statistic right there and my p-value. A couple of things. I like to do it by hand like this, and then I do like to do it on the calculator, and I like to double check that the numbers match up. So this said stat. Yep, there's everything that I plugged in. And my calculator, I bet if I scroll down, my calculator is going to have a different degree of freedom. I took the conservative approach and just did n-1 or 30 minus 1 and got 29. My p-value is 0.0086. That is low. That is less than 1%. You would say if the p is low, reject the hoe. With the p-value, here's my conclusion in context. With the p-value less than 1, this is statistically significant. We reject the null hypothesis. We can conclude that beta blockers, let's see, I'm going to reject this and conclude this. We can conclude that beta blockers probably do lower a person's blood pressure. Or this is evidence to say that beta blockers do lower a person's blood pressure. I can also look at the confidence interval. We are 99, and this is my confidence interval. I can make my calculator do that. I can do that by hand. We're 99% confident that the true mean difference, so this is how much they differ. The true mean difference in the patient's heart rate with the beta blockers is between negative 10.64 and 0.439. So that's the true mean difference is between there. Okay, let's try another one. Same idea. This is Pam. Pam is shopping for apartments, 1-bedroom and 2-bedroom apartments. So she's got the price of 10 2-bedroom apartments and 10 1-bedroom apartments. She thinks the 2-bedroom apartments are significantly more than the 1-bedroom apartments. Perform a test. So I would need to define my variables. I'm going to let mu sub 1 be the mean cost of a 1-bedroom apartment. Mu sub 2 be the cost of a 2-bedroom apartment. See if the 2-bedroom is significantly more. My alternative, or my hypotheses, the null is always assume no change. Assume that they're equal to each other. Okay, the alternative, that the 2-bedroom is more than the 1-bedroom. There's my hypotheses. My assumptions: random, independent, normal. Let's see, for random, it does not say that this, oh it does. This is a random sample of 10 apartments. I would say that, SRS. Independent, are they independent of each other? They are likely independent of each other, but maybe not. Maybe they're from the same apartment building. So that is an area of caution. I would at least mention that in context. Normally distributed, well, 10 is less than 30, so central limit theorem doesn't quite apply here. I would have to actually look at the distributions. I would have to actually make a box plot or a histogram and check for skewness or outliers. Let's see here. I should name this. This is a 2-sample t-test. Some people say a 2-sample t-test for means, or a t-test for 2-sample means. It's all the same thing. The things that are significant there are the words 2 and t. Okay, I'm doing my mechanics. This way. I would type these in as lists in my calculator, and it would tell me all these numbers. That's what I would get if I did it by hand. I would get 9 degrees of freedom because it's 10 minus 1. That's a conservative approach. If I did it in the calculator, I would get the same things. I'd get this for t, this for my p-value. Degrees of freedom, if the calculator does it, 17.8 or 17.90. Yeah, you can put that. You can also put this conservative approach. If you're going to put the conservative approach, I would probably do it as 10 minus 1 if you're doing it with the card. That looks good. Oh, my p-value says it right there. 0.029. So that is a small p-value. This is evidence to reject the null hypothesis. I would reject the null hypothesis. And conclude that I do have evidence to say 2-bedroom apartments are significantly more expensive than one-bedroom apartments. If I were doing the same thing with a confidence interval, I would have all the same assumptions. I would have the same definition of terms. It would be a 2-sample t interval, and I would plug things into the calculator. I get this confidence interval. And so that means the difference in the cost of the 2-bedroom and the 1-bedroom. So the 2-bedroom apartment is going to cost more than the 1-bedroom. The true mean difference in cost is between -$3 and positive $159. The true mean cost. So we are 99% confident that the difference between the 2-bedroom and the 1-bedroom apartment is between -$3 and $159. Okay. I've got these out of order. That's okay. There's one from the AP right here. This is another one very similar to what we did with cholesterol. I've got a placebo. I've got cholesterol. I've got 2 groups. This would not be matched pairs because I can't match them up like this. It's not matched pairs. Instead, it's a 2-sample t-test. You can either do the lists, or it's got mean and standard deviation already done for you. And again, this one doesn't have part A, B, and C. It just has a question. Is there convincing evidence at the 1% level? So this person who received full credit, and you would have about 15 minutes to answer a question like this. Full credit. They defined their variables. Important things are hypotheses. They've got them right here. It does say, is it effective in reduction? So that's why this is one-sided and it's a greater than symbol. They name the test by either the formula, that's what they did, the formula, or you could name it, in this case a 2-sample t-test is what they did. They found their test statistic, they found their p-value, they have their degrees of freedom, which probably just came right off the calculator, because if they were doing this by hand, they would have 9 degrees of freedom, just like we had in the one right above it. Real quick, just because we need more practice with this stuff, p-value is 6%. There's a 6% chance of getting a sample this extreme. That is not a low p-value. That is not significant at the 1% level. That is why they did not reject the null hypothesis, or they failed to reject the null hypothesis. They failed to reject the null hypothesis. Nope. There is insufficient evidence with a p-value of 0.062 at the alpha level of 1% to conclude that the cholesterol drug level is effective at reduction. Assumptions are important. Rarely are they going to ask you for the assumptions, but if they straight up just ask you one question like this, you know they want all of it. You know that they want you to do all of these things. Simple random sample. They're independent of each other. And then they're checking for normality. If it's greater than 30, central limit theorem tells us it's normal. Sample size is less than 30. That's why they made the box plots. Okay, it's just another example. I feel like we've looked at a lot of these lately. A couple problems for you to try. Here are a couple multiple choice. And, oh, it's up above. And one that was an AP question many years ago. To try also. So hope you guys are doing well, and we'll talk soon.